Hi everyone. In today's lecture we are going to explore about analytic functions. So recall from our last lectures that if you have a complex valued function like f of z, you say that if you can define a derivative of f of z, you would define it like this: f prime of z limit delta z goes to 0, f of z plus del z minus f of z by del z, just like real variables. Now, since this z is a complex value and f of z is a complex valued function, we also saw in our previous lectures that we can write it like this: u of xy plus I of v xy, right? And now what we want to do is that we want to find out such conditions that will enable us to understand whether this derivative over here, whether this exists or not. That means we want to find some condition that is necessary and sufficient for this guy to exist. So let's try to do it, and the conditions that we're going to find out at the end of our calculation are called Cauchy Riemann conditions. So let's get started with the calculation. Now if you can recall that this derivative, we are trying to define it on a complex plane, right? So this is the complex plane, this is the real axis, this is the imaginary axis, and so on. So in the last lectures we said that this derivative should exist regardless of your direction of approach. Let's say this is the point of interest, and no matter which way you come, you will always get the same value if you try to compute this quantity, because this z was what, x plus iy, right? And you can obviously write this as a parameter t, as a parametric curve. So no matter which curve you take, in which way you go, if you try to approach this point of interest, you will always get the same value. That was the intuition behind this derivative thing for it to exist. Now we are using this idea. What we're going to do is that first we are going to write f of z in terms of u and v. Okay, so let's try to do that. So let's write f prime of z as limit of del x goes to 0, del y goes to 0. I'll explain why I'm writing it this way. And here you will have u of xy, sorry, not just xy. Let me just write it down. Minus, okay, I think I should probably write it in the second line instead of just writing through this drawing. So yeah, so this is our f of z plus del z, this guy, and for f of z you have u of xy plus I v of del x plus, sorry, it should be just x and y. And in the denominator it was del z, so it should be del x plus I del y, something like this. And the reason I'm writing it the del x goes to 0 and del y goes to 0 separately is because if del z is written as del x plus I del y and del z is going to 0, that means x and y, both of them are going to 0 separately. So that's the rationale behind writing this thing like this. Now what we want to do, we want to carry out this calculation by using two different directions, and then we want to equate them, right? So let's say our first approach will be along the real axis. That means along the real axis, this means del y is equals to 0 always, because you are changing things or you are moving on the real axis itself. Okay, so if we consider this, then this expression over here, let's call it an expression I becomes f prime of z limit delta x goes to 0, because y is always 0, and we have u of x plus del x comma y plus iv x plus del x y, then you have a minus, and I'm just gonna multiply the minus directly. You have u of x of y. Also note that along the real axis, since you are changing things on a real axis, right, you will only get del y equals to 0. That means you are changing things on a real axis. It's not that you are moving things on the real axis, but you're changing things. That means when I say you are moving, that means you are changing things or changing the parameters. So that's why the y itself is not 0. Okay, so try to visualize that. Let's say you have something like a curve like this, and if you project it over here, again this is not a complete this is not completely related with the complex valued functions, but it's just a pictorial way of seeing things, that if you take this segment and you project it, and you can change the x while not making any change in y. Obviously this should be a parameterized thing, because there is x and y, both of them are involved. And if you try to visualize this in terms of the real variable calculus, then any function of xy is just a surface in the z plane, and you can keep your y and you can change x and you'll move along this surface and stuff. So that's what is happening over here. Okay, so this is important, that you are changing things along the real axis. Okay, or you are approaching in such a way that you are not changing your y, you are keeping that y fixed and stuff like that. So now let's write the next line, and it should be minus ux minus iv xy, and in the denominator we will only have our x. Right, now let's try to collect the real and the imaginary terms and see what happens. If you collect the real terms only, and if you collect the imaginary terms only, it will be b x plus del x minus bxy by del x, and you can see that this is nothing but the partial derivative of u with respect to x, which is also written as ux in shorthand manner, or it can be equivalently written as del xu, whatever the way you want. And this is just a partial derivative of v with respect to y, also written as vy, or you can write it as this. Okay, now what you have over here, you have du dx plus I dv dy, like this. Okay, now this, let's call this equation 1 that we got from equation I. But now what we want to do, we want to change, this is the approach 2, so let's write that first. That means now we are changing our direction, approach 2. In this approach, what we do is that we don't make any change in x, we only make changes in y. So we are taking a route, or so to say, we are changing things along the imaginary axis, and for that we are getting del x equals to 0, but del y is still changing. So now f prime of z should be limit del y goes to 0, and you would have your u of x y plus del y plus iv x y plus del y minus u of xy minus I of vxy. divided by I del y. I is a constant, so let's keep this outside, and we finally have limit y goes to 0. You can collect the real and the imaginary parts together, and you will have this u of x y plus del y minus u of x y del y, and here you will have a minus sign, and then inside that minus sign, I'm just jumping down some steps here, but it's pretty straightforward algebra, and you can take an I as well. That means you can factor out an I as well. So this is just x y plus del y minus vxy del y, and yeah, that's pretty much it. So you can keep this 1 upon I, and this is again du by del y, the definition of partial derivative, and this is dv by dy, or u of y v of y. So this is 1 upon I times ui plus, sorry, it shouldn't be plus, it's minus I vy. Now if you multiply this thing with 1 upon I, and you use the fact that minus I square is just equals to 1, what you get for 1 upon I is just that minus I. So you have this minus I uy, and then you have a minus minus plus, and there's I square, right? Okay, did I say that right? I need to check. Okay, let's just do it normally. So this is 1 upon I, and here you should get a minus vy, because this 1 upon I, it's there, so I is in the denominator. You write 1 as minus I squared, then you use the I in the denominator to factor out one of the i's in the numerator, you get a minus I, and so on and so forth. So this is minus common, you have vy plus I uy, right? This, let's say this is equation 2. But what was the condition for the derivative to exist, right? That it's independent of the way you approach it. That means the way you make changes in x and y, that means the direction itself. So why did we take only directions where we are either changing x or either changing y? Because it's more simpler. It's more simpler to do this calculation and see it. So since we had this condition that the derivative should be the same or it's unique regardless of our way of approach, we can say that equation 1 over here and equation 2 over here, they're the same equation, right? So if we do that, what we have is ux or del u by del x, whatever you want to write. I prefer this method, that I will prefer writing in this way. So equation 1 gives us vy, and then we have this minus vy, and there's a minus I uy. Okay, I think there is a sign mistake by me. Yeah, I think I made a mistake over here. That is a mistake in sign. So let's see, let's try to recheck our calculation. As you can see, all these signs are over here, they are correct. So what went wrong? Let's try to trace it. There is this 1 upon I, it goes over here, that's great. Limit del y goes to 0. Okay, this is fine. Oh, okay, now I see. It should be a plus sign. This is the mistake over here. It should be a plus sign. So to rectify this mistake, what we have to do, this should be a plus, and this should be a plus, yeah, and this is it, vy minus I uy. Okay, So that should be our right hand side. So this is wrong, this is not the correct thing, there is a sign mistake in it. On the right hand side you should have Vy minus I Uy. And if you compare the real and the imaginary parts now, compare the real and imaginary parts, you'll have Ux equals to Vy and Vy is equals to this should be Ux, it shouldn't be Y, it should be X. Sorry, this should be Y and this should be X. Yeah, that was an error, so sorry about that. Ux plus IVX, right? I made a mistake over here as well. I wrote it as Y, it should be X. Sorry about this. So finally what we can write this as Ux is equals to Vy. This is one of the conditions, and the other condition is that Vx is equals to minus Ui, and both of these conditions together are known as the Cauchy-Riemann conditions. So why bother with the Cauchy-Riemann conditions? Well, they guarantee, that means if you have a function f of z which you have written as, let's say, like this, assuming that they have a first order partial derivative at some point, let's say the point is z, which is denoted with some x and y's. If they have a continuous partial derivative over there and u and v are such that they will satisfy these two equations simultaneously, then at that point f of z will have a derivative, and this is a sufficient condition. And the necessary condition is that if you have a function, that means the necessary condition is kind of the reverse of this thing. The condition I just spoke about is that if you have the Cauchy-Riemann conditions, then it will hold if f of z is differentiable. Okay, that means we know about the Cauchy-Riemann conditions, we know about some function, and if we check that the real and imaginary components of the function are satisfying the Cauchy-Riemann equations, then we say okay, this is a necessary condition. And a sufficient condition is that when you have these u's and v's, that means if they exist first, and it also turns out that the partial derivatives of u and v exists as well, then if you combine them in this manner, then if this portion, the portion with u and v, if they possess the partial derivatives at some point that is denoted with x and y's under z, and they also satisfy this equation as well, then f prime of z, that means the derivative of f exists. Okay, so if you put all this gibberish together, you get a pretty straightforward theorem, and that theorem tells you that if your f of z, so this is something that is coming from the necessary and sufficient conditions. That means you take these necessary and sufficient conditions together, you combine them, and you get a theorem, and the theorem tells you that if your function f of z, that is given by u I v x y, if it's differentiable, that means you can get some f prime of z, at z is equals to some point, let's say x plus iy, which is a region inside our complex plane, if and only if the partial derivatives, that means ux, uy, vx, vy, are continuous. And so this is one thing. So when you say if and only if, that also means necessary and sufficient condition. Okay, so this continuity is necessary, and then the sufficient part would be coming from the Cauchy-Riemann conditions. So that's why we write as that if these partial derivatives are continuous and satisfy the CR equations, I'm writing in shorthand the Cauchy-Riemann equations, then f of z is differentiable at point z, which is given by x plus iy. So this is the theorem, and we are not going to prove it. Now we want to see some consequences of these Cauchy-Riemann conditions, and even though we said that we want to discuss about analytic functions, we haven't come to that point yet. We will come to that in a bit. So a consequence of this Cauchy-Riemann equation can be seen from the fact that if you have some curve that is labeled by, let's say, u is equals to c1 and vxy, let's say, equals to c2, you can easily show that using Cauchy-Riemann conditions, one can show that till this is a gradient. Okay, so this gradient of u dotted with the gradient of v would be actually equals to 0. What does that mean? So let's say you have this complex plane, this is our complex plane, and let's say this is our u curve, okay, in the complex plane, and let's say this is I don't know, the v curve, something like this, or it can be like this, whatever. So the gradients of u and v will always be perpendicular to each other, because the dot product, through the dot product you can see that whether the two vectors are perpendicular or not. This is one way to see them. So why taking this gradient? Well, what we wanted to show is that if you have this u and v that satisfy the Cauchy-Riemann conditions, then the level these two curves that are seen in this diagram, this can be called as level curves, and these level curves are orthogonal to each other, even though it's not pretty apparent from this figure and stuff. So this is one way to see one of the consequences of the Cauchy-Riemann conditions. Also, one can derive a second order partial differential equation called Laplace's equation from the Cauchy-Riemann conditions. If we assume that u double x, that means the second derivative of u and v, I mean the second partial derivatives of u and v, they exist, then you can take let's say this Cauchy-Riemann condition, one of the Cauchy-Riemann conditions, then you can take the derivative of u of x with respect to x, and similarly x with respect to y. In the next line you can write it as uxx minus, let's say, sorry, not minus, is equals to del square b dy dx, like this, because partial derivatives are interchangeable. Now you use the other Cauchy-Riemann conditions, that means vx is equals to minus uy, right? So this is ux is equals to minus del y. What you have over here is vx, but what you can do, you can replace this vx, or the first derivative of v with respect to s, with u of y. So what you have ultimately is that minus u double x, that means the second derivative of u, and you get the second derivative of y, u with respect to y as well. So you just pull them back, pull this thing on the left side, and voila, this is the Laplace's equation. Similarly, you can show that this is also true, and together you can write it as del square u is equals to 0, del square v equals to 0, and these are Laplace's equations. And in fact, these u and v's which satisfy this Laplace's equation are called harmonic functions. That means if you find some function that satisfies the Cauchy-Riemann conditions, then you can use them as a solution for this kind of PDE. Alright, now while discussing complex numbers, we went to polar coordinates as well. So is it possible to write Cauchy-Riemann conditions in a polar coordinate? So polar coordinate, we want to see the form of Cauchy-Riemann equations. So I'm not going to show you the proof over here, but this is pretty easy and straightforward to do. This is the Cauchy-Riemann conditions in the polar coordinate, where u and v, both of them are functions of r and theta. Okay, so this is pretty easy. You just find the derivative, that means the partial derivative with respect to x and y in terms of r and theta, and you are done. Okay, but let's not discuss the proof over here. Rather, let us move on to something more interesting, and those things are called analytic functions. So what are analytic functions? So let's say you have a function f of z, and you want to know whether this is an analytic function or not, right? So we say that a function f of z, a function f of z is analytic at a point in the complex plane. Let's say the point is given by z naught if f of z is differentiable. Notice this word, differentiable. Differentiable. So when is a function f of z differentiable? When it satisfies the Cauchy-Riemann equation at a certain point z, right? So that's why we discussed Cauchy-Riemann equations earlier. So at point z naught, if f of z is differentiable, and it is not only differentiable at that point, but it is differentiable in a neighborhood of z naught. That means you are adding the Cauchy-Riemann conditions at some point z naught, but you are taking this z naught point, not only you are taking this z naught point, but also you are adding a small neighborhood of it. That means if you have a function that is differentiable at this point and also inside this neighborhood, then that function is analytic. If you have a function that is only differentiable at this z naught, but if you draw a small neighborhood and inside that small neighborhood that function is not differentiable, then that is not an analytic function. So there is a very subtle difference. So the definition would be a function f of z is analytic at a point z naught if f of z is differentiable and sorry, I shouldn't write and. If f of z is differentiable at z naught and around its neighborhood, or you can say epsilon neighborhood, whatever you want. So this is where these definitions of neighborhoods, region, all these things comes into play. Okay, so this is the definition of analytic function at a point. Okay, and if your function f of z, if it is analytic at every point in a region, so now let's say you have a region like this, let's say this is our region, and you have a function that is analytic in each and every point. But what do we mean by each and every point? That means at every point and its small neighborhood, the function itself is differentiable. If that is true, then we say the function f of z is analytic over this region or in this region, in a region, if it is differentiable, and if it is differentiable at every point and its epsilon neighborhood. That means if you say, let's say these are my points, and f of z is analytic at all these points which make up the region, then f of z is just analytic over this whole region and stuff. So let us see an example that is a very dramatic example. So this says that you have f of z that has a real part x plus alpha y whole square plus 2i, that means the imaginary part, as x minus alpha y. They ask you that can you find such alphas that will make your f of z analytic. Okay, so let's try to see. The first thing is we have to see the Cauchy-Riemann conditions, and using the Cauchy-Riemann conditions we can first determine whether the function itself is differentiable or not. So the Cauchy-Riemann conditions were ux equals to vy, so this is our u, this is our v. Ux would be just 2x plus alpha y, and vy would be 2. You have this x gone because you are taking derivative with respect to y, so this should be a minus alpha like this, and if you solve this, this should give you 2x plus 2 alpha y is equals to minus 2 alpha. So 2 are gone like that. We have to sort out this alpha, so x is equals to alpha, let's say minus alpha or something, 1 plus y, right? So this tells you that alpha is minus x divided by 1 plus y, like this. Let's see the other Cauchy-Riemann conditions, because there were two conditions and both of them have to be met simultaneously. That means ux should be equals to vy, but at the same time uy should be equals to minus vx. Okay, so vx is equals to minus uy. This was the second condition. So let's do it, and if you take vx, it should be just 2, and minus uy would be 2x plus alpha y, and there would be alpha over here, right? Something like this. Yes, it would be something like this. And now you have 1 equals to minus alpha x plus alpha square y. So you have a quadratic equation for alpha. Now you can solve it as well. If you solve it, this will be minus x plus minus 4, it will be a and it will be c, so this is just 4y divided by 2. What is a is just y, something like this, right? Oh no, I made a mistake again, I think. Yeah, v of x, oh no, Okay, that's fine. Yeah. Okay, so everything's fine. I thought I made a mistake. So if you use these two again, what you end up having is that, because this alpha and this alpha, they're the same thing, they should be the same thing. If you use these two, if you make them equal, then you should get two conditions like this. That is, the alpha square would be 1 and only on the lines. That means if your alpha square equals to 1, only then these Cauchy-Riemann's conditions, ux equals to vy and uy equals to minus vx, both of them are satisfied simultaneously, or whenever x plus minus y is equals to minus plus 1. That means x plus y equals to minus 1 and x minus y is equals to plus 1. If you take points in these two lines, only then they are satisfied. Otherwise, the Cauchy-Riemann conditions are not getting satisfied. So that's why you say that the derivative of this function that we are discussing in the example, the derivatives exist only on these lines, but when it comes to the question whether the function is analytic or not, the answer is that the function is not analytic anywhere. Why? Because they are analytic on this line, let's say x plus y equals to minus 1, but they are only analytic on this line, not on the neighborhood of the points that reside in this line. That means you take a point over here, you draw a neighborhood. Since only at this point the functions are differentiable, that means the Cauchy-Riemann equations are satisfied, but on the neighborhood they are not. So that's why we say they are not analytic anywhere. Okay, and in some context, analytic functions are also called holomorphic functions as well. This is equivalent to analytic functions. They mean the same thing. Now, since in this example we saw that, let's say you have a point and around the neighborhood the function is not analytic, or at that point the function is not analytic, or the function might be analytic. So can we classify these points using the properties that we learned from the function's analyticity? The answer is yes. And if you have a point where a function fails to be analytic, then those points are called singular points. So the first thing we want to discuss is called a singular point. It's a point in the complex plane. Let's say the point is denoted by P, which belongs to the complex plane, where your f of z, or the function of interest, is not analytic. For example, 1 upon z square can be a function which is not analytic at z is equals to 0, and this 0 is a singular point for this function. Okay, a regular point is such that in those points the function is analytic. So these two definitions are inverse to each other. And finally, let's define another thing called an entire function. What is an entire function? It's a function, it's a type of function, or it's a function such that it is analytic at each point in the entire finite plane. That means you take your finite complex plane, the entire complex plane, okay, and it is such a function that is analytic in the entire finite complex plane. Examples would be e to the power z, sine of z, cosine of z, blah blah blah, like this. Okay. So this is a very basic discussion on what is an analytic functions, and in future we will talk more about it. Before we finish off, let us return to this Laplace's equation that we discussed over here. Where was that? Okay, there it is. So as I said, that if you can find some u and v's that satisfy these equations, they can serve as a solution for the partial differential equation that is given by over here. Now these are also called harmonic functions, as I mentioned before, and if you can find such u and v's, this u and v, they are called the harmonic conjugate of each other. And if you know u or v, then you can use the Cauchy-Riemann conditions to find the other. So that means, let's say you have a PDE and you know one of the solutions and you want to find out the other solution, so you can use the Cauchy-Riemann conditions to find them pretty easily with the help of basic algebraic techniques and basic integration and stuff. Okay. And you might ask, okay, why are we discussing all these analytic functions, differentiability and stuff like that? Well, it has application in almost each and every area of physics. That's the first thing. Also, a mentionable application that was first seen of this analytic functions was actually in fluid dynamics. If you are familiar with the incompressible law of fluid, that means what do we mean by incompressible? Let's say you have this something like a pipe, you have some fluid over here, and let's say this is flowing, okay, over here, and the incompressible means that your density it remains the same. So if you use that condition, you can see that the divergence of the velocity itself, it vanishes. That's what incompressibility means. Okay. And if you have a fluid that doesn't rotate while it's flowing from, let's say, A to B, then it also, the velocity field itself, this is the velocity field, the velocity field itself doesn't have a curl, let's say. So if you say this velocity field, also we are thinking this whole setup as a two-dimensional setting. So instead of drawing the cylinder, I should have drawn a plate like this, that where the fluid is moving. So you can incorporate these two pieces of information, that means the flow of the fluid, something inside called a complex velocity potential. And let's say this is your complex velocity potential, and you have a real part and an imaginary part. This part is known as the velocity potential, and this is known as the stream function. So let's say this is BP, velocity potential, this is the stream function SF. And in fact, this Laplace's equation also occurred in electrostatics as well. If you are familiar with the Maxwell equation, let's say del E, this is actually Gauss's law, a part of Maxwell's equation, so that's why I called it as the Maxwell equation. And let's say it's a source-free equation, so that means there is no source, so the divergence of E would be 0. And if you use the relation that E is the negative gradient of the V, which is a electric potential, right? So if you use that over here, this is nothing but del square V equals to 0. So So this is also Laplace's equation and stuff. So from here you can also see that you can use this analytic functions theory, the Cauchy-Riemann equations, all these stuffs to find a solution for these things as well. And we will see that how to do these things in future. For now, we want to keep these theories in at the back of our head right now, and in our near future we will see some applications. So this will be it for today, and in the next from the next lecture we are going to focus on multi-valued functions, and we'll return to analytic functions later in this course. Thank you.